Hello everyone, welcome to this video. In this video we are going to look about more properties, in fact the group properties whenever we have isomorphisms. So suppose we have isomorphism phi from the group G to the group G bar, then what do we have? We already know that this group G and this group G bar, they have many properties in common, right? And moreover, we can say that if two groups they are isomorphic to each other, then any property that can be expressed in the language of group theory is true for one group. Suppose it is true for this group, then it is also true for this group, and vice versa. And moreover, this is the only reason why algebraists speak of isomorphic groups as equal groups or the groups which are same. So in this case we would say G is isomorphic to G bar. So by saying this thing, they mean that the groups they are either equal to each other or they are either same, right? So what all properties which are similar to each other do these isomorphic groups have? This is the next question. So for this we have several other properties. If this phi, as I've told you, represents an isomorphism from the group G to the group G bar, in that case the first property tells us that now we have we already know phi from G to G bar, that is an isomorphism. So that means it is 1 1. So that means it is onto, correct? For these two properties here, because it is 1 1 and it is onto, so therefore its inverse would definitely exist. Now this inverse would also be an isomorphism, and it would be an isomorphism from the group G bar onto the group G, right? So this is the first property here. Second property tells us that if G is abelian, this would happen if and only if G bar is also abelian. So by abelian, what do we mean? All the elements A and B in G, they would commute with each other. This would be true for all A and B belonging to G, right? So therefore we would say G is abelian if and only if G bar is abelian. So in one way we are saying that AB is equal to BA. This would imply phi of A, phi of B is equal to phi of B, phi of A. And conversely, if this thing is there, we have this thing. So we already have done the proof for this thing in the previous videos, right? So using this thing here, we can prove the second property. Okay, next one is G is cyclic if and only if G bar is cyclic. Now they are saying the first group is cyclic if and only if the second group is cyclic. So let us assume that the first group is cyclic. So that means it would be generated by some element A from this group only, right? So let's call that element to be A. So in that case, this G would be equal to the group which is generated by this A. So we already know if G is generated by A, this would imply G bar is generated by phi of A, the image of this element A under the map phi. And conversely, if G is generated by this phi of A, so that would mean that if this G bar is generated by phi of A, then that would mean that G is also generated by A. So it means that if G is cyclic, so G bar is also cyclic, and conversely if G bar is cyclic, G is also cyclic. So we have also studied about the proof of this result in the previous videos, right? So moving forward on to our fourth property here, it tells us that if K is the subgroup of the group G, then the map of this subgroup under the map phi, so phi of K, which consists of all those elements phi of K, small k, such that small k is a member of capital K. So taking the mapping phi of all the elements of this subgroup, so that forms another set which we are calling by phi of capital K. So this phi of capital K would also be a subgroup for this G bar. You can test this through the subgroup test, right? Assume that K is a subgroup of G, then you know for two elements A, B inverse would belongs to this G, this K, right? if you have A and B taken from K, then AB inverse would belong to K. This would surely be there because we are assuming this thing. Then using this thing, you can prove that if you take two elements of such kind, phi of A and phi of B, so we need to prove that phi of A into phi of B inverse, this also belongs to phi of K, right? So how this is done? This is very simple. Phi of A multiplied with phi of B inverse, what is this thing? According to the properties of isomorphism, we may write this to be phi of B inverse. Again, using the operation preserving property, we may write this to be like this, where what is AB inverse? AB inverse belongs to K. So this we have written as phi of some K, where K is some element of the subgroup K. So therefore this thing also belongs to phi of K. So this is what we are saying, and therefore by the one step subgroup test, this is a subgroup of the group G bar, right? Moving forward on to the fifth property, we have to prove that if K bar is a subgroup of G bar, right? If K bar is a subgroup of G bar, then phi inverse of K, this would contain all the elements G from K such that phi of G is a member of K bar. So this phi inverse K is also a subgroup. So this is exactly the converse of the fourth result by taking the mapping now as the inverse mapping. Now we are taking a subgroup from the group G bar, and then we are from this subgroup we are applying the inverse mapping onto it, and we are getting a subgroup of the group G. So you can prove this in similar manner, or you can directly use the property 4 here and the property 1 here in order to prove 5. Correct? For the next property here, it states that if we have the center Z of G, which is the center of the group G, right? So then they are saying if we apply the mapping phi onto the center of G, we would obtain the center of the group G bar. How cool is that, right? So you can again prove this property using the property that we have studied, that AB is equal to BA would imply phi of A, phi of B is equal to phi of B, phi of A for all the elements A and B belonging to G, right? So this is all for this video. You can try the proofs yourself. They are very simple. So I hope you understood the properties well. Well, that is it for this video. Thank you for watching.